Hi, I'm Patrick and I'll give you a quick tour of our work Network Fusion for Content Creation with Conditional INNs. This is joint work with Robin Rombach and Björn Ommer from Heidelberg University. State-of-the-art models show great performance. However, they require massive amounts of computational resources. As a rough estimate, a single training run of models like Big Gun, F-Unit or BERT take about 2 weeks, resulting in electricity costs of €300 or an equivalent of 400 kilograms of CO2 emissions. Note that this assumes that you already know the hyperparameters for your task. This goes so far, people have to join forces for crowd training to be able to train a single state-of-the-art model in slightly different configurations than the released ones. Thus, we ask ourselves how to optimally reuse the computational effort put into the training of these models. As an example, consider Big Gun, which is great for class conditional image generation. However, what if we are interested in a slightly different task, like text conditional image generation? It should be possible to reuse the image generation capabilities of Big Gun. Furthermore, there are also powerful models for representing other domains, like text in this example. Our main challenge is then to learn a translation between two representations produced by different domain experts. In general, this is a many-to-many task, as there are multiple realizations for a given query. Now that we have presented the general idea, we explain our method in more detail. Consider an expert model, which could be a classifier or a segmentation model, and split it into two parts. An encoding part, which yields a data representation, and a decoding part, which produces the output. Similar to expert 1, the second expert is also divided into two parts, which produce a representation and a decoding respectively. Note that both models are independent and can live on different domains like text and images. Due to the many-to-many nature of the translation process, we propose to model the transfer between the representations generatively. Our idea is to use a conditional invertible neural network and formulate the translation process as a mapping from a predefined prior to the representation of expert 2, conditioned on the representation of expert 1. Let us illustrate the training process with the example of text-to-image translation. Given paired data, such as images and their textual descriptions, we produce their respective expert encodings. Next, the representation of expert 1 is used as a conditioning information to map expert 2's representation onto the prior distribution, where the quality of this mapping is evaluated by the log likelihood. During testing, given a representation of the first expert, here the sentence "a yellow bird is perched on a branch," we sample from the prior and conditionally transform the sample into the space of the second expert. In our experiments, we show that our approach allows us to fuse BERT and Big Gun into a text-to-image model. The resulting model is able to produce diverse samples with high interclass variability and also distinguish between more low-scale features such as the color of a bird. Next, we exchange the BERT model for an image classifier, more specifically a ResNet. Based on the finding that CNNs trained on ImageNet are biased towards texture, we explored the representations of differently trained ResNets. For a vanilla ResNet 50 trained on standard ImageNet, we observed that conditioning on texture queries lead to coherent synthesis results, whereas conditioning on shape queries does not produce meaningful results. In contrast, using a ResNet 50 trained on a stylized version of ImageNet reverses this behavior. Texture-conditioned synthesis produces unrecognizable image samples, whereas shape queries lead to the expected synthesis results. Based on these findings, it becomes evident that different synthesis tasks ask for different experts. Edge-to-image synthesis depends on a shape-aware expert, whereas for inpainting, a texture-aware model is desired and leads to the best results. Similarly, the choice of different layers of an expert gives control over the variability of the produced outputs. Finally, we evaluated our approach on tasks which work directly with labels. This is possible because we do not require gradients of experts. Our results show good qualitative and quantitative performance for face modifications and unaligned image-to-image translations. For more results, make sure to visit our project page. Thanks and enjoy the workshop.
Hello everyone, this is our presentation for our workshop paper Text-Guided Image Manipulation via Local Feature Editing. My name is Tianhao Zhang, and this is a joint work with Lu Jiang and Weilong Yang from Google Research. So in this paper, we propose a new task called Text-Guided Image Manipulation, and the inputs for this task is a image and a text instruction. So we wanted to generate an output image by modifying the input image following the instruction given by the text. So here we have a text states that make middle right large cylinder small, and we have an input image where there is a large cylinder on the right part of the image. So we want to generate an output image where the cylinder is actually smaller, but the rest of the image are unchanged. The more well-studied area is image-to-image translation. So for our work, the core problem is actually how to apply text guidance into this image-to-image translation. And we wanted to basically use text feature as an operator to guide the image generation process. So here we propose a local feature editing method. Basically, we wanted to decompose the image generation process into two parts, finding out where to edit and finding out how to edit. So for where to edit, we wanted to highlight the region of the input image that needs editing. And for how to edit, we want to edit the highlighted area using the information given by the text. So take an example here. Given the text input make middle right large cylinder small, we want to use middle right to gain information about where to edit, and then we want to use make and small to get information about how to edit. And then we can first generate a spatial attention map to highlight the region that we want to edit, and then we can edit this highlighted region using how to edit information. Then we can generate the final image. Figure demonstrating the pipeline of the generator. Basically, the left part is the encoding parts, and then the top right part is the spatial localizer. So we use the first self-attention module to get text feature for where to edit, and then we generate our saliency map M. And then in the middle bottom part, as you can see, it's the local feature editor where we edit the cropped image feature using the instance normalization parameters, and then we add it back with the unmodified part, and then we put the entire feature into additional ResNet blocks to generate a final modified image feature, and then we decode this image feature into RGB image. So we are testing our method on two datasets. The first one is called CSS dataset. It's a synthetic 3D scenes dataset generated using the Clever toolkit, and it's used originally for retrieval. There are multiple text operations including adding, removing objects, and changing colors and sizes of objects. The second dataset is called CodeDraw dataset. Basically, it's derived from the abstract scene dataset, and it's used originally for iterative scene generation. And there is only one text operation in this dataset, which is adding objects. So here we show a qualitative comparison. The first column is the input image, and the second column is the input text. As you can see, our model can always generate the correct image based on the input image and text. However, for T-again, it almost just copied the input image. And for Geneva, even though sometimes it can generate images with modifications, but the modification is not following the input text instruction. Here we also show some intermediate results. As you can see, the second row specifies the where to edit words. So it's the result of the first self-attention module. Here we highlight words with an attention score higher than 0.2. As you can see, top center, top left, these are all words for specifying the location. And the third column is the second self-attention module, where the words contain mostly how to edit information. And then the fourth column is the generated spatial attention mask. Even though it's a little bit blurry, but it actually specifies the correct location of the image that we wanted to make changes to.
This is Hong Yuzhen from UC Merced. I'm glad to share our work image synthesis via differentiable patch retrieval. In this work, we aim to generate images from the scene graph representations. Given the input scene graph, our model learns to retrieve patch for each object from the real images. Our model then synthesizes the final image according to the retrieved patches. There are two issues in our work. First, the retrieval process is usually not differentiable. Second, the selected patches need to be mutually compatible. Therefore, our contributions are in the retrieval process. First, we use the Gumbel softmax trick to make the retrieval process differentiable. Second, we design an iterative retrieval process to select mutually compatible patch. Here we show an example qualitative results. Since our retrieval approach can be optimized by the GAN training, we can synthesize more realistic images. Thank you.
We present StarGAN V2, diverse image synthesis for multiple domains. Existing image-to-image translation methods require training multiple models, or produce only a single output for each domain. To satisfy both diversity and scalability, one can give a latent code and a domain label to the generator and impose the latent reconstruction loss. However, in this setting, the latent code alone cannot contain domain-specific information. To overcome the problem, we introduce a multi-head mapping network. We transform a latent code into a style code using a specific output branch of our mapping network and impose the style reconstruction loss. Unlike the latent reconstruction loss, our style reconstruction loss models domain-specific styles. Our style reconstruction loss enables the generator to produce images with more diverse styles than latent reconstruction loss. Using style reconstruction loss, our StarGAN V2 can successfully generate diverse images for all available domains. For more details, please visit our website.
Hi, I'm David, and in this short video I will introduce our paper. We propose a method for first generating a rough approximation of an image and then further fine-tuning it, so that it's close to what a user has in mind. For the first step, text-to-image synthesis, we propose a new model called TextStyleGAN. We enhance StyleGAN so that it can generate images conditioned on text. For that, we use a text encoder, we apply attention on words and image regions, and we apply an additional multimodal loss to ensure semantic correctness. Here you can see some generated examples of this model. To manipulate a generated image, we use image representation W as features and training classifier to find semantic directions in latent W space. We then add these weights to obtain the manipulation. Here you can see some examples of manipulating images in gender direction. If you want to know more, check out the paper or feel free to ask me questions in the chat.
We present a new method for one-shot face reenactment. Given a face with target expression, The proposed far-GAN model can produce realistic faces with required expression. Compared to the traditional face animation method, we only request a single image from source identity. We have no assumption about facial pose or viewing angles of input faces. We can also deal with complex background. After detecting facial landmark points, we fit both source image and landmarks to the model. The embedder learns to extract the pose information from landmarks, and then fit the feature to the transformer to transfer expression. Our results show that the proposed far-GAN model can produce realistic reenact face with different source faces and target expressions. Thanks for watching.
Hello everybody, I'm here to talk about generating object stamps, and this is work primarily by Yusuf Majati. So our task is to take a background, which is not in the training set, and a bounding box, and then create an instance of a particular class. And we want to be able to give ourselves control over that class, such that we can manipulate the texture, such that it matches the lighting, and the pose, and to be able to build up these scenes using objects of different shapes and textures. So how does this work? First, we have a shape generator, which takes in our background and the bounding box, and infers a mask. And then we have a second stage, a texture generator, which also takes in the background here as a conditioner, so that we can try to match the illumination of the object to the background. And you can see that we generate diverse shapes, and that we have some control over the texture, and that this matches the lighting too. Existing methods, like the Hong method, try to generate all of the interior of the bounding box at once. If we just try to copy and paste an instance with deep image harmonization, this typically tends to produce worse results too. Okay, there you have it, generating object stamps. Please come and talk to us, we'd be happy to start a conversation. Thank you.
Hello everyone, I am pleased to present our work learning to shadow hand-drawn sketches. This is the joint work with Suo Ruli at Project HAT and Dr. Adam Barkdal at UMBC. In computer graphics, cell shading is hard to get right, because the shadows must preserve binary appearance. It is either lit or not, nothing in between. It would be easily ruined by the smallest consistency. The goal of this paper is to shadow the given 2D line drawings automatically. The network builds the 3D information in latent space. The output of our network is just the pure shadow which can be edited by the artists. With our network, the artists can have a good starting point or a hint to shadow their art. We contribute a novel dataset which consists of 1,160 cases of sketch, shadow and mask, but we didn't use masks in this work. We have 26 kinds of discrete lighting directions in this dataset. We use synthetic data to train a light pre-processing deep learning model to normalize the inputted line drawings, making them have the same line width. This is the general workflow of our network. The line drawings are inputted into the encoder first. The lighting directions are embedded by a fully connected layer. We repeatedly add the embedded lighting directions into each stage of the decoder. The final outputs are binary shadows as in our ground truth. We also have two intermediate outputs to facilitate the learning process. Both of them are soft shadows. The final outputs, S1 and S2 from the generator, are penalized by mean square error losses. We add a total variation term in the final output loss to encourage smooth shadow boundaries. The input of discriminator is the composition of shadow and line drawing, and the lighting direction. The final objective is the sum of GAN loss and the loss of output S1 and S2. We build a relatively deep decoder to rebuild the 3D information in latent space. Whenever there is an embedded lighting direction inputted, we use film block to enhance the visual reasoning. When there is skipped connections from encoder, squeeze and excitation block is able to filter out the redundant information from encoder. The coordinate channel, which is marked as red after concat, is to enable the learning of 3D spatial information. At the end of each stage of decoder, except the final stage, a self-attention layer is added to enhance the holistic visual reasoning. We compare our work with Deep Normal and Sketch 2 Normal. The input of them are line drawings, the same as our input. However, their outputs are normal maps. To compare with our shadows, we render out the normal maps with thresholding at 0.5. Our results have accurate shadows in complex and multi-object line drawings. Also, our network learned the stylization of hand-drawn shadows while the others have the appearance that synthetic data has. When the depth of lighting source changes, our results have accurate and apparent shadowing changes. However, deep normal has inaccurate depth appearance in front lighting and side lighting, and sketch 2 normal suffers from complex line drawings. In backlighting condition, our results have rim light around object boundary, while deep normal and sketch 2 normal do not. We also compare with the baseline Pix2 Pix and UNet that trained on our dataset. We can see that Pix2 Pix architecture fails to reason the shadow, and UNet fails to generate binary shadows. Under the side lighting condition, we compare with a 3D test model ground truth. This picture demonstrates that deep normal has backlighting appearance when it is actually side lighting. Our result is most close to the ground truth and learn the smooth boundary of shadow from hand-drawn dataset. Despite the network learned from 26 kinds of discrete lighting directions, it can produce continuous shadows. There are more testing results in the wild in a wide range of style of line drawings. From the ablation study, we can see that, without the proposed modules in our network, the results will either have inconsistency, acne artifacts, or unrealistic shadows. Those are the failure cases and limitation of our work. First, we have slightly different shadows in different size of input. Second, if inputting a local part of an integral line drawing, the network couldn't reason the right shadows. Third, our network suffers with hard surface object. Last but not least, since our output is pure shadow, easy for artists to customize their own artworks like shadows in complex lighting source, half-tone shadows in comic style, and concatenating colored line art with shadows. The last image is the original art drawn by an artist. This is another example of our shadowing system applied to reshadow the artistic line drawings. Thanks for your time. Please refer to our GitHub repository for the dataset Encode.
Our work, Caligan, is a style and structure-aware Chinese calligraphy character generator. Chinese calligraphy is the composition of brush-written characters on paper or stylus. However, some characters become unclear or damaged when papers and stylus decay. This problem restrains calligrapher beginners from emulating masterpieces and designers from using masters' work. Therefore, we want to solve the problem of generating Chinese calligraphy characters. We form the problem as translating characters' image from one domain to another. However, existing method never exploit component information. Therefore, we modify a state-of-the-art game-based method by replacing its label embedding vectors by one-hot vectors and adding a component encoder. Experiments show our method generates better results. Our code and dataset is now public on GitHub.
Hi, I am Ayush from Adobe. I'll be talking about our work on image-based virtual try-on. So the task of image-based virtual try-on involves taking as input the image of a target model, a new in-shop cloth, and swapping in the cloth on the model to generate the try-on output. So a standard pipeline for image-based try-on consists of 2 phases. The first phase involves transforming the in-shop cloth to align with the pose of the target model to generate a warped cloth. In the second phase, the warped cloth is transferred on top of the target model to generate the final try-on output. So in this work, we proposed CVNet, a novel framework for image-based virtual try-on, and we break down the entire pipeline into 3 components, namely a coarse-to-fine warping component, a conditional mask generation component, and a texture translation component. These correspond to our warping and texture transfer phases respectively. So in this slide, we detail the network architectures for each of the 3 components. Next, we'll be talking about them in detail. The first step involves transforming the in-shop cloth into the warped cloth. Now, to better handle fine-grained intricacies during the swapping process, we regress the parameters of the spatial transformer network hierarchically in 2 stages, namely in a coarse-to-fine fashion. However, at inference, a single cumulative spatial transformation is applied on top of the in-shop cloth. Next, to better handle artifacts during the texture transfer process, we break down this phase into 2 steps. The first step, which we call the conditional mask generation, uses the segmentation mask of the target model and the image of the in-shop cloth to predict the resulting segmentation mask of the model after trying on the cloth. This mask is used as a prior to condition the final synthesis process of the try-on output. In the second step, called texture translation, we predict the final try-on output. This is done by using the conditional mask predicted in the previous step, the warped cloth predicted in the step 1, and a couple of texture translation priors. So these texture translation priors refer to components that are preserved during the virtual try-on process and should be transferred as is. We train this translation network with a dual and triplet strategy, and empirical evidence suggests that training with this strategy helps to better handle bleeding and occlusion. We extensively compare our proposed framework CVNet with CPBT, a recent state-of-the-art, on a wide range of image quality metric. Our extensive quantitative analysis highlights that CVNet consistently outperforms CPBT on all of the metrics. We also perform extensive qualitative analysis on a wide range of parameters. Our results show that CVNet is able to generate better quality of images, consistently handle occlusion better, generate skin better, as well as handle large variability in pose of the target model. Thank you.